All right, this week we're going to talk about notifications. And why notifications? Because in an IoT system, okay, so first of all, we have built a dashboard that we, can monitor a dashboard and look at, okay, what's happening in the system, which is fine. I mean, obviously, but then you don't necessarily want to look at your dashboard all the time, right? That is because there's certain interesting events that you want to be notified of. Let's say there's an intrusion happening. Your IoT system is detecting the purpose is that like home security, right? So then you want to get notified while you're actually not looking at your computer. So how do you get notified? You get notification through multiple ways. How do you get notification today? You could get a phone call. You could get a text message, or you get an email, or maybe your phone has a notification that pops up on the screen, right? So there's different things. And then one of the key thing is that the notification needs to be sort of where you are, so typically that implies that there's something that typically will show up when you're mobile. So that's why a lot of things kind of make sense to be sent to your mobile device. So that is one thing. But again, so the sort of the technology behind like email, and that's not mobile specific, but typically uh, you may want to get notified of an email happening on your phone. Text message is obviously tied to your phone. Um, that's basically mobile phone specific. And then the mobile device or your computer has a notification center, right? So you can get notifications delivered to your device. That is a typical feature your device will have. And so there's many different channels that we can notify a user of interesting events that's happening through the IoT system. Now, we've learned to deliver those things through HTTP, but the HTTP is just one way of delivering events, delivering notifications, and there are alternatives, and in fact, perhaps even better suited for IoT devices. So let's actually take a look at some of the underlying technologies. How do we communicate? And here's a little diagram here that shows some possibilities in an IoT system. So let's say you've got some microcontrollers such as Arduino, and Arduino that's perhaps running on a battery and tied to a physical whatever you're trying to do here in the field. And maybe it will communicate with a Raspberry Pi that's in the vicinity that serves as a device that aggregates data from Arduinos. This Raspberry Pi is more capable, is a mini computer basically, is more capable than Arduinos and or some other microcontrollers that you may use. And so there needs to be communication between these two. And then also there's, if you recall, we mentioned about the wireless protocols, how on what media that data can be communicated. That's a different level of concern that we're not talking about here. For example, there's a various different wireless technologies that allow you to transmit data from sort of a few feet all the way up to even a few kilometers. There's different wireless technologies that allow you to do that. Now, as far as then how do we communicate, send data around? So there are a couple of different choices. We're going to get into more details later. So, for example, MQTT is a so-called pub sub type of a protocol. We're going to look at that in a bit. And MQTT is a standard that allows many different sort of a resource constrained devices to communicate with each other. And the concept of a QTT uses a broker and client. The clients or could be subscribers or publishers. Um, just kind of get a little sense for now, and I'll talk a little more detail shortly. And so the information could be sent from Arduinos very efficiently and with a low power um, requirement to send the data to the Raspberry Pi, which could be serving as a broker for the message exchange. And this broker, if I give you an analogy, think of a stock brokerage. Then there's many people doing trades, and the traders don't need to know about each other. They just interact with the broker, and the broker will route the messages up, to the different users. So that's kind of a similar concept here. And the Raspberry Pi may be sent using a REST over HTTP to a little more powerful computer that's perhaps still local, that does some more processing and runs some full-fledged software that like your application requires a lot of resource consumption. Perhaps you have a local computer um, that you do that kind of processing, and that can even be sent to another level of sort of a local, more beefier servers or maybe your local data centers, and you can go all the way back to the cloud for even more heavy lifting if you want. That HTTP can be used over there. This is just some suggestions that could potentially happen. And then you may also consider using multiple cloud providers for resiliency in case one cloud provider somehow goes down, then your system can still be up and running if you have some kind of redundancy. So there may be a way for them to synchronize with each other if you have data in multiple places, and then they may be synchronizing with AMQP, which is another communication protocol that allows you to exchange messages efficiently. So there's a different choices there. Maybe your devices or your smartwatches, they communicate with your smart car through, here it shows an example that might most likely are using proprietary protocols, not necessarily the standard MQTT, AMQP. These are standard protocols, just as HTTP is. So here, some of these devices, the mobile devices, probably using proprietary protocols, that is fine. So you have those things communicating with other devices as well. And then you may also use HTTP or some other protocols to communicate to your servers. Now, here on the right-hand side, we'll talk about, there's actually a couple of concepts here. You have, we know what Internet of Things is. In this picture, it's kind of a little narrow view in terms of talking about just these things right here. But then we have cloud computing, and then we also have a fog computing. Fog computing is in the middle. The idea of fog computing is to minimize the bandwidth consumption when you have a ton of data coming from the sensors, for example, that you want to process them in the cloud. Instead of sending everything to the cloud, you want to do some local processing, maybe as much processing as you can, to reduce the cost and bandwidth that will be sent to remote servers very far away for processing. Instead, you can do some more local processing, make your system more efficient. You don't have to store as much data or process as much data in the remote servers. So that's kind of an idea of fog computing here. So it's a concept that came up almost 10 years ago that becomes more and more prominent nowadays with the IoT. Now, I just mentioned a couple of examples in that diagram about the communication protocols, and they actually, these protocols operate on the layer 7, just like HTTP is at the application layer. This layer 7, I recall that the OSI conceptual model, 7 layers, and this is at the very top layer. So you have HTTP that we've been using a lot. And then the alternative to HTTP is MQTT. MQTT, we'll take a look more into this, and this is designed to work with resource constrained devices like, basically your IoT devices. They are very, doesn't have a whole lot of processing power, and in fact doesn't have a whole lot of power either, right? Sometimes your devices are operating on a battery, so you want to do very little processing. So the protocol is designed for that purpose. And then you have AMQP, which is typically used for, it's also used for computer to computer or machine to machine communication. And this is usually designed without consideration of resource constraints. So most likely used among the beefy servers, so to speak. And then you have XMPP, which is Extensible Messaging and Presence Protocol. This XMPP is a very popular protocol that's used for chat applications. So you've the chat applications that you're aware of, a lot of them are really using XMPP behind the scenes. It's not because you can't use other things. Many of the protocols solve sort of similar kind of problems. However, the historical reasons, when those protocols were invented, there were not a whole lot of alternatives at the time. But then as time goes on, many of the protocols have caught on. They have enhanced, added more features. So sometimes you realize that those protocols can do more or less similar things, but they still have their strengths and weaknesses. They have sort of their focus, so they're not exactly equivalent. There's also data distribution service. This is also a protocol designed for resource constrained devices. But then the difference between MQTT and DDS, for example, is that MQTT is using a TCP as the transport protocol, the layer 4 protocol, just like HTTP is built on top of TCP. But then the DDS uses UDP underneath. Now, UDP is different from TCP. TCP is a reliable protocol. There has a built-in reliability for messaging, for basically for sending the packets. But then the UDP is a sort of, you send a packet, you don't really get a response, or you don't wait for a response. It's kind of fire and forget type of protocol. Well, the advantages is fast. However, the disadvantage is that your connection may be unreliable. And that may be okay in some situations. So you see the trade-offs. Do you trade performance for reliability, right? So you can't get both. And then another protocol is called a CoAP. CoAP stands for Constrained Application Protocol. And this protocol is interesting. This protocol is also designed for constrained devices. However, the goal of this protocol is to be compatible with HTTP. So you can use CoAP almost like HTTP, except that behind the scenes is dealing with constrained devices, trying to make some clever enhancements there. So this is an interesting protocol, although it's not very widely used. Like, the well-known, most popular really nowadays is HTTP and MQTT in terms of IoT, in the IoT world. And it doesn't mean they're the best protocols. It's that for many different reasons, they just got a very wide ecosystem. So CoAP is there. I think it's catching up, but it's also a very useful protocol. Now, we've studied the client-server model. Client-server model also can be considered called the request-reply model, like HTTP. Now, here's an example, sort of a review. HTTP, remember HTTP now we have actually 3 versions, 1.0, 1.1, and 2. So the most widely used and most popular nowadays is 1.1. 2 is coming up as more and more people are supporting it, more and more applications. 1.0 is historical, that kind of is very rarely used nowadays. So you got a client, you got a server. For example, the one in 1.0 is built on TCP. It's the TCP synchronization. It kind of is called a handshake. It does a handshake situation so that the connection is, it's kind of a few back and forth. So the connection is confirmed. And then so now they can talk over this TCP connection. And then the client will send a request and then wait for a response from the server. And then once that's done, closes the connection. So every request, it opens a new connection and closes right away. So that's 1.0. And then we realize, okay, it's not very efficient. Instead, in 1.1, we say, well, on that one connection, let's send multiple requests, which is called pipelining. So multiple requests are sent, and then we get multiple responses. But then the requirement of this 1.1 is they need to be received in the same order as the requests that are sent. So the order is maintained. Okay. In HTTP 2.0, that in that case, we say, well, let's relax the requirement of ordering a little bit for the purpose of gaining performance. So when the client sends multiple requests, the server can process them without waiting one to another. So as soon as the process one finishes, and they will send it back to the client, although it could be out of order in terms of the order of requests that are coming in. So which is, kind of you sacrifice a little bit of a constraint in terms of the ordering, but then you gain some more performance here. So that's HTTP 2. So it allows you to do asynchronous processing. And then CoAP. CoAP is also request reply. As I mentioned earlier, this is made to work with HTTP essentially. It's like HTTP. Now, except the underlying protocol is not TCP anymore, it's actually UDP. So it's a fire and forget kind of situation. The client sends a request and then the server responds. That's it. So of course, because of that, it requires a very low resources to process the request. It does not need to maintain a connection. So this is designed for resource constrained devices. An alternative to the request and reply model is the pub sub model. Now, pub sub stands for publisher and subscriber. Now, if you recall the previous week, we did a home security dashboard. Over there, we had to design a simple a message, sort of a message, what is called, and the message announcer. So if I open that up, so if I this message announcer here, you recall that we use a queue for each listener, and then whenever we got a message to send, we'll add that to the queue of that listener, and we're gonna announce it to everybody, like broadcasting. And so if we got 100 listeners, we're going to announce it to everybody. So we're doing this kind of maintenance here. And this is sort of a rudimentary way of processing these messages in a spirit. It's actually very similar to the pub sub model, okay? Except they're all in the same program. But in the pub sub model, you have three entities. You've got a broker, you have a publisher, you have a subscriber. Okay. Now, in this case here, the service is the broker, and the service also is the publisher. So we publish the event to this message announcer, which acts as a broker that handles the message routing, registering the listeners, and the listeners coming from the browser, right? So we have a client from the browser using the event source. That's the browser web API. And that is a client that basically will become the subscriber, essentially. Has the same idea as this, which is a listener or subscriber, same thing. So the publisher publishes data on a specific topic sent to the broker. The publishers are not aware of any subscribers out there. It only sends a message to the broker. And then it keeps doing that. That's what it does. And then the subscriber is saying, well, I'm interested in this particular topic. So if there's a message on this topic, send it to me. That's what it's about. So when it subscribes, say, I want to subscribe to this particular topic. And then the broker, whenever it gets a message from the publisher on that topic, it will route that message to the subscriber which subscribed to that topic. Okay. So this PubSub model, you've already got a little taste of what it was like without rudimentary message announcer and handling that server-side events. Okay. Let's do a bit of a comparison. We mentioned of some of these protocols, and so the REST HTTP is a request response model, request reply or request response, the same thing. You got a CoAP, which is just like HTTP, except it is for resource constrained devices. And then we have AMQP, that is also request response. Not necessarily that's the only way to communicate. It's just that AMQP supports it. XMPP also supports it. And then you have HTTP 2.0. That's obviously there's a support there. That's the kind of the origin of HTTP. And the PubSub model is so popular that if you realize, except the REST HTTP on 1.1, everything else has support for PubSub. This PubSub model allows you to process requests asynchronously, and it has an advantage in terms of latency, in terms of handling a huge amount of connections. That's why the PubSub is very popular nowadays. And this is the standards body. So there's a couple of standards body that standardizes many of the protocols here. You got IETF, OASIS, those are, and the OMG as well. So the IETF and OASIS, they're kind of the most well-known. And then the transport is the layer 4. Okay, these are the, remember the OSI? Layered model of the web or the internet, that you have the layer 4 is doing the transport of the lower level packets. And then the higher level application protocol is about how the application communicate with each other. But underlying that, you got choices of a TCP or UDP. Basically, you have two choices. So here, as you notice, there's the difference. So I kind of explained this. Now there's something new here, the QoS. QoS is called the quality of service. Quality of service, I can give you an analogy here. So the post office, when you send a mail, you can choose some additional services. You can just mail a regular, first-class mail, put a stamp on it, and then you will be delivered. However, you do know that that kind of mail is not entirely secure. It may get lost. You don't have any kind of confirmation if the recipient has received it or not, right? The post office doesn't give you that. But if you say, I want to confirm that it's been delivered, then you can pay for certified mail, right? So that's a quality of a service. And then you can get an even higher level quality of service, for example, using priority mail. Priority mail, not just in the sense that it gets delivered faster, but it also gives you even more secure guarantee, even probably higher insurance as well. If in the case that it gets damaged or lost, you can get compensation for it. But obviously you have to pay more for that. It's an even higher level quality of service. There's more cost to post office to handle that kind of mail. So that's the kind of concept of quality of service. The same thing happens here in the digital world when we send the messages through a protocol. So, for example, MQTT defines 3 levels of QoS. We're going to look into that very shortly. And then you have a CoAP, which has 2 levels actually. MQP has three levels. DDS has about 20. So some other protocols doesn't deal with the QoS. It's all just treated the same way. Like like as if everything is a first class mail. There's no differentiation. And then the security side is these protocols. Of course, you want to handle, okay, how do you deliver your message securely? But you have to consider though, the security, the cryptography processing is resource consuming. It can be a challenge for the resource constrained devices. So, but it's a necessity, unfortunately. But there's ways to improve that. But anyway, the most popular security built into the system is on the transport layer. You got the TLS. SSL has been outdated. So today, the newer standard is the TLS. And then you also got DTLS, which is TLS for UDP protocol. Um, and this security, there's active research going on to how do we handle security in a sufficient manner, but then less resource consumption for the sort of resource constrained devices like IoT systems. So that is an area that's actually still a challenge today. And then this little diagram here shows typical usage of those protocols and kind of put them into the position where the places where you might see those protocols used more often. And so kind of mirror to the previous diagram there, you got the bottom level, Internet of Things. And messages get delivered to the fog computing devices through MQTT, CoAP, and XMPP, okay? And then when the fog computing devices get sent message to the cloud or within the cloud or across different clouds, they're most likely use AMQP. And then you got a REST HTTP could be used in all different layers as well as a TDS. TDS is, it's actually a very interesting protocol, but we're not going to talk too much about this protocol. It's not as widely used or widely known, of course. And then so, of course, everybody knows about HTTP is most widely used protocol, but it's not necessarily the most efficient protocol for all the scenarios. So for example, MQTT is designed for IoT devices. So this is very suitable for resource constrained devices. Now, we're going to take a little closer look at MQTT because we're going to use this in our examples actually. And this is a protocol, as I said, is very popular. And so we want to know a little bit more about this. If you design IoT system, I mean, really, you should know about MQTT. So here, this little illustration, just a little bit more detail about this broker pub/sub model and what is actually happening with the MQTT. A publisher publishes a message to a broker. So this is it sends a published message. And the message type is basically publish, and then you have an ID of the packet, some kind of number specified, and then you have a topic and name, for example, topic/1. And then you can define a QoS, 1, 0, or 2. We're going to look closer at what that is. And then you may also define a retain flag. What is that? I'll explain shortly. And then the payload is really your actual message. Maybe a message like this, or maybe a JSON, most likely a JSON when you deal with this. And the message sent to the broker, and the subscriber will receive the message. If it's subscribed to the same topic and the message comes in, the broker will send this to the subscriber. And the subscriber, when it subscribes, it needs to specify also a QoS as well as a topic, okay? The QoS, there's 3 levels for MQTT. 0 means best effort. Like the first class mail is gonna try and it may get lost. So that's what's happening. That's a 0. 1 is saying, we're gonna guarantee this to be delivered at least once, like a certified mail, but not exactly certified mail because it can occur multiple times. There can be duplicates. And then level 2 is, well, the highest the service. We're going to deliver the message exactly once. Okay, it will be delivered and there will be no duplicates. Okay, so the resource consumption goes up from 0 to 2. The retain flag is indicating to the broker whether you want to store the last published message for new subscribers. So if this flag is set, the broker is going to retain the last message from the publisher, even if there's no subscribers, it's going to always retain that very last message. The advantage of that is if there's a new subscriber coming in, they're going to get that very last message or the very latest message right away. Okay. Even if the publisher goes away, for example, somehow went offline. So the subscriber is going to get at least the very last known value of a, let's say, a temperature sensor. Okay. So there's situations where you might want to use that. And there is also people are working on enhancement of MQTT designed for sensor networks, in the sense that we're going to even reduce the resource consumption even more by not using TCP. Remember that trade-off between the performance or the power consumption and the reliability. So this MQTT SN uses UDP as the transport. So that's the other alternative protocol. Okay, so we've seen the concepts of the different protocols, and let's actually take a look at MQTT in action. So as we know, for the MQTT to work, you need a broker, and then you need to have a publisher and a subscriber. In fact, your same program could be a publisher and a subscriber if you want to. Okay, they don't necessarily have to be separate programs, but the broker typically is a separate program. And the broker, there's open source MQTT brokers you can install on, on Linux, on Windows, whatever. One of the best known open source brokers for MQTT is called Mosquito. So Mosquito, okay, this one. So this is open source. You can definitely use this and get this installed into your system if you want to. Now, for our purposes, we're not going to install a broker. We're going to use a free one that's already there, a public broker that's basically made available for people to test. So Mosquito actually provides a test broker, is actually under this domain test.mosquito.org. And if you go to that page, that site, it will explain, it has a little page explain what this is about and the different ports exposes. So this is the domain this actually exposes on these different ports where you can communicate with it through the MQTT protocol. Okay, so how do you communicate with it? So you need a client. So the client we use, now of course we have language bindings for, any kind of language, basically the most popular language you can see, there's a MQTT client you can use. And of course for us, we're going to use Python. So in Python, the client that you can use is called a PAHO. So PAHO, again, is a obviously open source library this project provides MQTT clients of various different languages. This project is sponsored by Eclipse Foundation, which is in the same league as Apache Foundation for a lot of the high quality open source projects. So here we're going to use a PAHO, and the way to do this, essentially, let's take a look at the main function here. So you create a client object, and then you're going to define a onConnect, the onConnect function. The onConnect function is where you can print out some status if you want. But if you're not interested in, here, this is just for the purpose of um, showing you what you can do. So initially, you will need to make a connection. It's not doing anything that useful. It just prints out a message. And when it's successful, we say, well, connect it to the MQTT broker. So in fact, if you don't care about this, you can ignore this. Okay. So then you're going to connect to your broker's host name. And there's other parameters that you can specify here. We're going to now here just take the default. Okay. The port 1883 is a well-known port for MQTT. So that is the port actually that's unencrypted, like HTTP versus HTTPS. So if you want to use TLS, then the port is 8883. So those things are actually all exposed right here. So you see 8883 is a MQTT encrypted. Okay. There's many other variants here too, but so if you do need a specified port, you can specify right here. The default will work just fine here. And then we're going to call the loop start. The loop start, basically what that means is the program will enter into a loop, and the loop is in a separate thread. So we're going into a multi-threading again. So this is really how many of the programs work. You have to deal with the concurrency because you want to do multiple things at the same time. So this is going to basically process network traffic. It will pilot, so this will go into a separate thread, so it will not block. And so here, the next thing we want to do is want to run something to publish messages. So here, we just have this is for testing purposes. We're going to actually have a while true forever loop. And we're going to keep publishing messages. And then each time we'll publish a message with a message number, which is a count. And this will keep increasing as this loop goes through. And so the primary thing to publish messages use this publish method of the client object. And here we specify a topic and a message. And then you want to retain this or not, the remainder. So recall the retain flag, as I explained about the, excuse me. So right here, the retain flag, as I just explained, whether you want to store the last message on the broker or not. And then we can check the response from that publish. So if the response is 0, then we will say that's successful. Otherwise, something failed. Okay. So that's to publish a message. And we're going to run this shortly. Let me explain the subscriber side. And the topic here, we just kind of defined a global variable. Say, hey, this is our topic. Okay. The topic is hierarchical. You use the slash to separate. You can, in terms of subscribing to a topic, you can use a pattern if you want to subscribe to multiple topics. So, so you kind of think of the Unix file system, hierarchical structure. So this is, or like yeah, that's a good analogy there. So that's the topic here. We're going to publish our messages to this topic. Now, of course, you can use many different topics if you want. Now, the subscriber side. One thing I want to mention though, to get this Paho library, you need to install it. So you install this library, Python library, Paho-MQTT. That's the one to install. So over here, similar, kind of a pretty much similar to the publisher side. So we're going to create an object for the MQTT client, and we may define the property on connect. And now the onConnect here does a little extra. So in the onConnect method, we're going to subscribe to a topic. Okay, this is the subscriber. And then we define our message function. The on message function, this is basically, okay, once you get the message from the broker on that topic, what are you going to do about it? So this is the processing. So here we'll only just print this out. Okay, we're printing out the topic from the message as well as the payload. So we'll get the payload from the message as well. So remember when we publish, we'll publish a message here. This is what we're publishing. And then we're getting the payload here in the subscriber. So, okay, so let's actually run this thing. So we need to run both, and then you'll see there. So let's run the publisher first. QTT publisher. So this is running, right? Sort of we have a statement that prints out this message. We're sending the message to the topic. This all goes through that Mosquito broker. Now let's run our subscriber. Now, once it starts from the message 24. That's when the subscriber joined. It will start from that message. The old messages, they were just discarded. But since we use the retained, right, the retain is true. So the very latest message will be retained. When it's joined, it will use that message. So for example, if I stop right here, we have message 52, right? And if I'm going to start the subscriber now, it will get that message 52 because that's stored on the broker because the retain flag. Okay. And my publisher is not even running. We're not sending any new messages. If I start sending new messages now, it's going to continue. It will show up in the subscriber right away. You see that? Okay. So that is how MQTT works. Very simple because we have a library to use, and then to use it, it's very straightforward. So we can incorporate this function into our application to use MQTT to send the messages to whatever client that you're interested in. So essentially, let's say, remember there are home security dashboard where the our devices send signals or events to the client through the server-side events. So here, what we can do if we want to use MQTT is whenever there's a motion, for example, or whenever the arm status has changed, and then we'll send a message to the MQTT broker. And then our UI application, the JavaScript, it will use MQTT client to talk to that same broker to listen to those messages. You see, that's the alternative way of doing it. Instead of using SSE, we can use MQTT to achieve the same function that we wanted to do, okay? And in that case, though, if you use MQTT, you'll realize the client, like the UI application running in the browser, does not need to interact with your backend service at all. It will only need to talk to the broker to get the messages, right? And in fact, that UI client can also send the message to the broker too, like to change the arm status that will turn the LED on and off. That can also be done similarly. We'll send a message to the broker, publish it, and then your service will basically process the message as a subscriber. So you see, a single application can be both a publisher and a subscriber. Those are just basically different roles. So that you see how that can work, even though the publisher and subscriber, they don't have a direct connection. They don't need to know about each other. And so that's the advantage of that asynchronous model. As this is MQTT, what allows you to do, right? So that's what I'd like to explain in this lecture. Thank you.